This is part 2 of the chemical analysis topic. It's GCSE AQA chemistry, and this is a dual and triple award topic. Going to recommend, as always, that you try the activity pausing the video as you go. So in this particular video, we're going to look at how we can use chromatography to identify whether a substance is pure or impure. We're going to look at how the science of this actually works, and we're also going to look at how we set up the apparatus to make a suitable chromatogram. And we're then going to focus on how we can interpret chromatograms. Specifically, we're going to calculate the RF value. So there is a required practical within the course that fits in with this. You can see lots of information here relating to it. I'm going to focus on the method, and I'm going to recommend that what might be good for you to do at the moment is pause the video here, try to work out why we're doing what we're doing. And we're going to pick out a few examples from the method once we move on with the video. So we are drawing a horizontal pencil line 2 centimeters from the edge of the chromatography paper. Why would we draw it in pencil, not pen? Well, I'm going to talk about that later in the video, but you must remember it's a pencil line that you draw across. We use a glass capillary tube. These are incredibly narrow tubes, which allows us to get very small sample sizes for what we're analysing. Actually gets a lot harder to analyse a chromatogram effectively the more sample that we use. We're going to label each spot. We're going to label it in pencil for the same reason we drew the pencil line in pencil. But why do we label it? Well, it's really important that once we've set up our chromatogram, we know what we are analysing. So we're going to make that clear on the chromatogram itself. For the next one, we're going to pour water into the beaker to a depth of approximately 1 centimetre. And you'll notice that the pencil line is 2 centimetres above. That's a really important consideration to make. We don't want the paper, or we don't want the water line to go up the paper beyond the pencil line, because the pencil line is where we're going to add our samples. And if that went straight into the water, it would dissolve into the water in the beaker. It wouldn't be carried up the paper. We're then going to paperclip the chromatogram. Why might we do that? Well, the chromatogram is chromatography paper. And as it gets wet and it gets soggy, it's going to start to collapse. So the paperclip helps to maintain the height. It stops it collapsing into the beaker. Alternatively, you can use a wooden splint and hang that and hang your paper from that in the centre. And the final bit that I'm going to pick out here is not moving or disturbing the beaker during this time. That's really important because any agitation of the solution might actually alter your results. So now let's look at analysing. Let's go through, have a go at A, B and C. So the baseline drawn in pencil, that's down there, and we've got the line drawn on. We have got the solvent front, which is B. This is how far the liquid rises. So you will see a point on the paper which is wet and above it is dry. It's really important that you label that solvent front and draw the line across when you finish the chromatogram, because once it's dried, you won't know where it's got to. And finally, we're going to look at how we can calculate the RF value for X, Y and Z. Well, to do that, you need a ruler and you need to take measurements. So from the baseline to the solvent front, we have got 86 millimetres on this particular paper. If I look at how far each of the others have travelled, the dot as a result of X has travelled 78 of those 86 millimetres. Y has travelled 34 and Z has only travelled 15 millimetres. Now the RF value is essentially a ratio of how far the sample has travelled compared to the length the solvent has travelled. So if we take a look at the examples here, if I look at the RF for X, 78 divided by 86 gives me an RF value of 0.91. If I then do the same with Y, That's 34 divided by 86, giving me an RF value of 0.4. And finally, we have got Z, which has travelled 15 millimetres. So 15 divided by 86, we get 0.17. So let's go to the question that I've already touched on already. Why did we draw that baseline in pencil? If we go back to it, you can see here that we've got our dots of ink that have been put on for X, which has gone and separated out into X, Y, and Z. Now, it's separated because the ink dissolves in water. So if I drew my baseline in pen, that pen would form a part of the chromatogram. That ink would start to dissolve, rise up, and separate on the chromatography paper. For that reason, it wouldn't work. We wouldn't be analysing the sample that we're actually interested in. So however long the chromatogram ran, and whatever the total difference between baseline and solvent front, the RF value for a given substance would be the same. Why? Well, on this one, what we're really looking at is the ratio will be the same. If this is also important, if control conditions are maintained. If we do this with the same concentration and we do this at the same temperature, the RF will be the same, because the RF is a measure of the ratio between the distance the substance moves and how far the solvent front moves. With any specific substance with a specific solubility, that ratio will not change. So let's have a look at this. We have got A and we've got B. We've got the solvent front travelling 12 centimetres. A has travelled 8 of those 12 centimetres. B has travelled 3 of those. A has a higher RF value. What can we deduce? Well, A is more soluble. That's important to know. And I'm going to talk more about why in a second. Let's work out the RF values. We can do that. We've got the figures. So A, the RF is 8 divided by 12. That's 0.67. And for B, it's 3 divided by 12. So that comes to 0.25. If something has a higher RF value, it means it's more soluble. Let's try and explain why that's the case. If something's more soluble, it can stay dissolved in the solvent for longer. And if it can stay dissolved in the solvent for longer, it can be carried further up the paper. So that's really what we're looking at there. And finally, to finish off this video, what conclusions can we draw about this chromatogram? Well, there's lots that we can take. Green is the most soluble for the reasons we've just spoken about, because the green dye travelled much further up the paper, has a higher RF value. By that same token, red is the least soluble and blue is obviously in between. We can go a little bit further as well. 2 of these substances are pure. B contains only 1 dye. It contains the green dye. It only forms 1 spot, so it's a pure substance. C is also a pure substance made up of just the red dye. However, A is an impure substance. A is a mixture of 3 different dyes: the green, the blue, and the red. There are lots of chromatography past paper questions out there. It's good to go and have a look at those to see what sort of questions can be asked that will rely on the knowledge that we've built on in here. But that takes us to the end of this video. Thank you for listening and goodbye.